Hi, this is Tom Brower from the Hydrologic Engineering Center. In this video, I'm going to go over the 5 simulation types available in HEC-HMS. The simplest and most commonly used simulation type is the simulation run. A simulation run is the combination of a basin model, a meteorologic model, and control specifications. The basin model describes the hydrology on the land surface. The meteorologic model describes atmospheric conditions over the basin. The control specifications define the temporal extent and resolution of the simulation. Some special options available in a simulation run include precipitation and outflow ratio scaling, an option to save model states at the end of a simulation, and an option to start the simulation with states that were saved from a previous run. The next simulation type is a forecast alternative. Forecasting typically includes the simulation of past and future conditions. In a forecast, a look-back period is used to calibrate the model before moving into the forecast period. Because forecasting is typically a time-sensitive process, the forecasting alternative includes many specialized zone and initialization editors to help rapidly calibrate the model. The optimization trial can automatically estimate parameters when observed streamflow data is available. The optimization trial uses an objective function to measure how well the computed and observed flow hydrographs match. The search method uses the objective function as input to an algorithm that determines how to adjust parameter values to find the optimum match. Optimization can provide good estimates for some parameters, such as infiltration parameters or initial conditions, unit hydrograph parameters, base flow parameters or initial conditions, and some routing parameters. Optimization can be used in the middle of the calibration process, that is, after initial parameter estimates have been made and before manual fine-tuning to arrive at final model parameters. In the example on this slide, the optimization trial has been used to maximize reservoir pool elevation by adjusting storm area, location, and orientation. Next, the depth area analysis. The frequency storm and hypothetical storm options in HEC-HMS can be used for estimating flows for a design storm, such as the 100-year storm or other return interval. Part of the design storm procedure usually involves reducing point rainfall depths by some depth area relationship. It is common to assume the storm area is equal to the drainage area at the analysis point, then reduce the point rainfall depth accordingly. The depth area analysis is helpful when there are multiple analysis points in the basin. For each analysis point, HMS determines the area upstream and reduces the point rainfall depth according to the area upstream. On the left, we see a basin with multiple locations of interest highlighted in red. On the top, we see the locations have been specified in the depth area analysis component editor. On the bottom right, we see results for each analysis point, including the drainage area, the peak discharge, and the time of peak. Finally, the uncertainty analysis. The uncertainty analysis uses the Monte Carlo method to estimate uncertainty and model parameters. The uncertainty analysis creates many alternative models of the watershed using an automated sampling procedure. Each sample model is created by sampling the model parameters according to their individual probability distribution. Each sample model is then simulated to obtain a watershed response corresponding to the sampled parameter values. All of the responses from all of the samples can be analyzed statistically to evaluate the uncertainty and the simulated watershed response. This concludes the presentation on the 5 simulation types in HEC-HMS. For more resources on HEC-HMS, check out the HEC-HMS documentation website.